Welcome to our next lesson in physics. Today, in keeping with our block on pneumatics, hydraulics, we're now moving into a different aspect of the physics of fluids. Remember that air is considered a fluid along with water and oil and any other kind of thing that can be manipulated from the outside and does not retain its shape. So today we are going into the study of air, but instead of looking at pneumatics as we began with, we're going to talk a bit today about aerodynamics. Now, aerodynamics is a field of science that looks at the ways that objects move through air. Now, aerodynamics is closely related to another subject, which we would call hydrodynamics. And hydrodynamics, of course, would refer to how objects move through a fluid or a liquid. So both of these share very similar principles, but today we're going to focus on the idea of aerodynamics. Now, to begin with, we have to ask ourselves the question of how many times have you thought how amazing it would be to be able to fly? In fact, humans have been thinking that for a long, long time. Everybody who looks up in the sky and sees the freedom of a bird probably has a little bit in the back of their head saying, I sure wish I could do that as well. Well, people have been thinking about that, and of course that has led over human history a lot of people to ask, well, how do we actually go about doing that? Can we get ourselves to a point where we can fly? And the answer, of course, in our modern world is we have many ways that we can get up and fly. But going back to the beginning, we should ask ourselves, who were some of the key people who helped us understand the basics of aerodynamics, and out of that, an understanding of how we can achieve flight? Well, the first person I want to talk about today is the brilliant artist, scientist, mathematician, all-around genius of the Renaissance, Leonardo da Vinci. Leonardo is someone who definitely asked the question, how could we create human flight? And he spent hours and hours not only studying, but doing drawings and doing diagrams in order to try and explore the idea of how can humans achieve flight. So Leonardo used to spend time, he would go to markets and he would get birds that were being sold as pets, and he would bring them home in their bird cage, and he would spend hours looking at the anatomy of the bird itself. Oftentimes, this would result in him opening the bird cage and allowing the birds to fly after he had given a great deal of study to how their wings were structured. He would then let them fly so that he could observe the actual fundamentals of what was going on. Not just looking at the beauty of a bird in flight, but really asking the question, how does that work? Well, of course, we know that birds are able to fly because they have wings. And wings have a very specific type of a structure that allow them to work. So what did Leonardo discover in his in-depth look at bird wings? Well, the first thing, of course, is that anyone who knows anything about birds would tell you that a bird has hollow bones. Birds with their hollow bones are able to then have the structure of a bone with a lot less weight attached to it. And we're going to see that, of course, in the question of flight and aerodynamics, there's always going to be a factor of weight. And so the first thing that makes birds flyable is the fact that they have, over time, evolved a very, very lightweight skeletal structure. The second thing, of course, would be to understand how does a feather work? So, of course, when we think about a bird's feather, we once again have a hollow structure. That internal or that central spine that makes up every feather is, of course, also hollow, but is hard enough to retain its shape while being still flexible enough to have some movement. Now, of course, when we look at the rest of the feather, we have a bunch of almost hair-like structures that come out from that central spine. And all of those, of course, are also very, very lightweight. But interesting enough to us in understanding aerodynamics, we can also look at the way that a feather is shaped and the direction that those hair-like structures go. When we think about a bird's feather, we realize that everything is moving in the opposite direction of the way that the bird is going to move. So the point or the tip of the feather is always going to be at a far distance from where the front of the wing is going to be, meaning all the feathers are oriented out away from the leading edge of the wing. Now, of course, birds aren't the only animals that are able to fly. We have bats. And of course, bats evolved a lot of their similar structure from animals that were flying all the way back in the dinosaur era. Now, in the case of either a bat or a dinosaur or even a dragon wing, we have again a lightweight skeletal structure. And instead of having feathers in between, there would be some sort of flap of skin. Still having the same principles, and one of the key principles that we would say about all of these is that the leading edge is thicker than the far edge. So we could say that a bird's wing is larger around the shoulder or around the part that meets the air first, and then tapers down to a thin edge at the end. So this evolution of wings has basically shown us that nature has a very clear way in which it is going to use aerodynamics to allow certain animals to be able to fly in the air. And obviously they have to be lightweight enough to be able to get off of the ground, but also they have to have a very clear aerodynamic structure in their wings. Now, of course, different birds have evolved different structures to their wings, their bodies, their tails. Everything about a bird is different depending on what the purpose of that bird's flight is. So here in Hawaii, we have a Eva bird, which is a very famous, it's also called the frigate bird. And the Eva is a bird that is very well known for going deep, deep out into the ocean, flying for really far distances and having to be able to survive without necessarily landing on the water or landing on ground for a long period of time. So obviously a bird with these characteristics would have evolved a very distinctive and very, very efficient flying shape. And so when we look at an Eva bird, we see that the way that the bird's wings are structured are once again a very strong shoulder moving up. The bones that come off of the shoulder are going out to a point. And in the case of the Eva bird, it tapers out to a fairly pointy sort of end of the wing. The other thing that's important to understand in the structure of an Eva bird that allows it aerodynamics is the way that the body of the bird is shaped, and of course the way that the tail is shaped to help the bird maintain balance and to help it guide itself in different air and wind patterns. So a bird has to have a combination of abilities in order for it to fly. First of all, there has to be a way that the bird is able to flap its wings in order to get itself off of the ground. And so flapping has to do with aerodynamics of creating force that goes downward, and that force that goes downward is able to create lift. Because we know that if we push down on air, we're going to get resistance from that air. And if that resistance that we are getting from the down flap of a wing is balanced in a way by the lightness of the bird, then a greater resistance is going to have enough lift to actually pick the bird off of the ground. So flapping ultimately has to have a certain amount of balance of surface area of the wing, lightness of the bird, and of course the ability of the bird to be able to have the strength and the structure to flap hard enough to lift itself off the ground. Now once a bird is flying, then the aerodynamics shift. The aerodynamics of a gliding bird have to do with the way, of course, that the air is going to flow over and under the wing. And we'll talk about that in a moment because that's the key of aerodynamics. So our birds, we realized, all the way back from the days of Leonardo da Vinci, have already evolved all of these different aspects in order to be aerodynamic in flight. And so what does that mean? What is an aerodynamic shape? Well, certainly we can see that to be truly aerodynamic, or hydrodynamic for that matter, there are certain shapes that just naturally are going to work better in controlling the flow of fluids, whether that fluid is air or water or anything else. There is a very clear way that a shape that comes to a point is going to be able to be more efficient in dividing that fluid so that the fluid will move above and below it, or to the two sides. Rounded and no edges is an important feature in something that is aerodynamic. Any type of edge that we create, or any type of blunt face at the front of any object or creature, is of course going to reduce the aerodynamics. Air can catch on an edge, and when air catches on an edge, it's going to reduce the flow of that air above and below whatever it is that's moving through the air. We also know that as something tapers off on the backside, that will also help its aerodynamics. So when Leonardo was first coming up with his ideas for human flight, he had to study these structures of wings, and he came up with some very great ideas about how to fly. Unfortunately, we as humans are quite heavy with dense bones and dense mass in our bodies that make it very, very hard for us to be light enough to have any kind of wing structure that we could make that could actually carry our weight. Originally, Leonardo had ideas about how we could create some sort of flapping mechanism. But what he learned was that birds are designed very well. They have tremendous ability or a tremendous amount of chest muscle and strength in that area that allows them to flap their wings. We simply don't possess that. So even with the mechanical devices that he came up with, and people who followed him came up with, ultimately, we just don't have the strength in this middle area to be able to flap hard enough to get ourselves off the ground. Eventually, though, we did figure out how to come up with things like a hang glider. And a hang glider essentially gives us enough of a wingspan and enough rigidity in the structure of a hang glider that we can be able to go and jump off of a higher site and glide for a period of time. So, we have figured out a certain level of human flight, but we certainly have not figured out how we could get off the ground by flapping. So that is our loss as human beings. So how does aerodynamics really work? Well, we have many things that are aerodynamic. If we look at something like a bullet, it is shaped in a very aerodynamic form and therefore is able to speed through the air with a great deal of accuracy. Once again, a point that is tapered. It has all rounded edges. It's essentially cylindrical coming to a point. And of course, as it pierces through the air, it's going to stay on target as long as it is consistent. Well, before bullets, of course, people had figured out how to make an arrow, another very aerodynamic object that even shares the word. An arrow takes us a step further because an arrow also includes the idea of adding fletching, or the feathers at the end of an arrow, which of course give it stability. Now, many objects as they move through the air then are going to have a very, very similar shape if they're going to be successfully aerodynamic. When we look at something like a brick flying through the air, no matter how well you throw that brick in a straight way, the fact that a brick is rectangular and therefore has a very blunt face and has a bunch of edges is going to make it the opposite of an aerodynamic shape. Throwing a brick, it would be very difficult to keep it accurate and on target and moving across a plane. So of course we see the brick as a not aerodynamic thing. Now there was a man named Bernoulli back in the 1600s who came up with a principle that allows us to understand some of the basics of aerodynamics. And the easiest way to understand the aerodynamics of, for example, an airplane is to look at the speed at which air passes the object and how the object is shaped in order to allow some air to pass more quickly and some air to move over the object more slowly. Bernoulli's principle essentially tells us that there is energy and a relationship between the speed of moving air or fluid and the amount of energy that is released in that process. So to put it fairly simply, the wing of an airplane, if we were to look at it from the side, is what we would call an aerofoil. The design of an aerofoil has variations depending on how thick it is in the front, how long it is, how much it tapers to the back, how much curvature there is in it. All of those are factor. But the very simple idea of a foil and what allows an airplane to get lift is the fact that the front edge is thicker than the back edge. And the front edge, although rounded, not blunt like our brick up there, it is designed in a way where the bottom is generally either flatter or is slightly concave. The top edge, as we see, is thicker and rounded and then comes down to a tapered end. The very simple way that a foil or an airplane wing works is that the air moving below the airplane wing is going to be moving faster than the air that moves over it. And because the air below is moving faster, it is going to create lift. The top part of the wing, the air is moving differently, and it's going to create a pattern of turbulence in the air behind it. But that lower part of the wing is going to be moving quicker, the air is going to be moving quicker below it, and therefore that increase in airspeed is going to be the factor that allows a wing to help an airplane lift off. So there are 4 important things that we need to know about a foil. And this can be an aerofoil, like an airplane wing, or this could be a hydrofoil, like a fin that allows a ship to go up at a certain speed and lift off of the surface of the water. Or it could even be as simple as that's really the design of a dolphin's pectoral fin, which really is a way that nature is telling us that that's a good idea because it works well. So there are 4 things that we would see in a foil or an aerofoil for an airplane wing. We have thrust. There has to be some way that in order for it to fly, there has to be some way that this wing or foil is moving forward. Well, tomorrow we'll talk about the different ways that aircraft are able to develop thrust. But in one way or another, there's got to be something that is impelling this thing forward. Now, the opposite of thrust is drag. And drag is caused by friction. So ultimately, as anything moves through a fluid, whether it's a wing through air, or it's a foil through water, or if it's the dolphin's fin, there's always going to be a certain amount of drag created as the object moves through the fluid. There's always going to be a certain level of friction, and as that friction builds up, it is able to slow down whatever it is that is moving. Now we have 2 other factors that are always going to come into play as well. There is always going to be the weight of the object that we are desiring to lift. And of course, there has to be enough wingspan and enough surface area in a wing in order to create enough lift to be able to take that object off of the ground. And the lift, of course, is going to be influenced by the shape of the lower part of any kind of a wing. So these 4 things working together have to find a perfect balance in order for something to be able to fly. There has to be enough thrust to move the object forward. There has to be a limited amount of drag that is going to create friction and slow the object down. There has to be a light enough weight that this wing will be big enough and have enough surface area to be able to create the lift, which will have to be strong enough to be able to get this thing off the ground. Obviously, all of these factors coming together are what is going to result in a successful flight. Well, when we return, we'll look at some of the early people's developments in airplane flight. What were some of the methods that they used to provide their thrust, and of course, what was the way that they shaped these wings, and what were the ways that, just like our arrow, how did they provide stability in order to make these machines work? So we'll return with our next lesson on aerodynamics by looking at some of the early aircraft that were developed.